All right, thanks. So I'm going to, even though this is a direct continuation of the topic we discussed, which is entropy bounds, so I try to motivate the idea that there could be a general bound on the maximum entropy of matter coming from the generalized second law, coming from the fact that if you drop this matter into a black hole, the black hole is only increased by a certain amount of area, and so that should tell you that the entropy of the matter that you lost, well, can't be bigger than that. That sort of works for a certain class of matter systems, like a ball of radiation. It doesn't seem to work when gravity is strong, like in the universe on large scales and deep inside a black hole. The covariant bound is a statement that does seem to work, and on the other hand, cannot, in fact, be motivated from black holes alone. It's not something that can be derived. And so let me switch perspective in the sense of just simply stating what appears to be true, and then we can see to what extent there's evidence for it and what it all means. So let me start by actually saying a few words about the holographic principle, which is closely related to the statement of these entropy bounds. I would say the holographic principle, when we say holography now, we almost always mean the ADS-CFT correspondence, and I don't mean that. I'll describe later how that fits into this scheme of things. What I mean by it is something that's both far more general and far less specific, far less powerful so far, unfortunately. So the holographic principle is, I would say, a relation between the geometry of space-time and the information content of space-time. The covariant entropy bound is sort of the phenomenological manifestation of that relation. You can't have more entropy than the area in regions that I will explain how to construct. Are there any questions? It reduces to the kind of statements that we were trying to make earlier in those cases where those statements are actually correct, so ball of gas and so on, but it actually keeps working deep inside a black hole or in the universe on large scales. So let me start by simply stating the bound, sort of quickly give you an idea of what it says, and then I'll go through it again a little more carefully, and we'll check all those examples that gave us trouble earlier on with the space-like entropy bound. So, and again, do ask me questions anytime. So here's the statement. So I want you to keep in mind that in these pictures, time is going to go up. It's not always going to be important to draw space-time pictures. Earlier on, we were dealing with purely spatial statements, instants of time, and I was drawing, the geometry at that instant. Here, I'll always have time going up, light rays going at 45 degrees. So this is a spatial direction. This is time. I obviously have to suppress some dimensions. So for example, this thing here that looks like a circle, you should probably think of as really a two-sphere, something like the walls of a room at an instant of time. And so here's the statement. So take any two-dimensional surface of some area A, and by two-dimensional, I really mean at an instant of time. So I have to specify both where the surface is in space, but also when I'm looking at it. It's just a fact about Lorentzian geometry that given any such two-dimensional surface, there are four null directions, four light-like directions away from it. Okay, you'd think a surface has two sides, but it actually has four light-like sides. Because you can send light rays to the inside and to the outside, but you can also choose whether you want to send them towards the past or towards the future. Okay, or you can think of light rays arriving from the past if you prefer to put it that way. All right, so this would be a sphere at an instant of time in Minkowski space, for example. And here are the four light-like hypersurfaces away from it. Now, they're called light sheets only under a certain condition, which I will explain. Right now, I just want you to sort of imagine them. This one here, this cone here at the top would be the 2 plus 1 dimensional hypersurface that's seen by the light rays that would be emitted by, I don't know, a bunch of laser guns shooting away orthogonally from the surface, from the walls of this room at this instant of time. Okay, and they go towards the center. And of course, I could keep going, but let them go through each other, but I'll explain why I don't do that. And then the same thing here. This would be a bunch of light rays that, in the limit of a spherical room, would be emitted by a single flash of light in the center of the room, and it would make its way out and hit the walls. And then finally here, these two larger objects here, that would be laser guns mounted on the outside of the walls of this room, sending light out into space. Okay, so this is, these are null hypersurfaces. Now, it's only called a light sheet if the cross-sectional area that's spanned by neighboring light rays is actually decreasing. Okay, so you can see immediately that the ones that are drawn in thick lines here are light sheets, and the other guys that go towards the outside are not. Towards the outside, the cross-sectional area is increasing. The spheres are getting larger and larger. Towards the inside, it's decreasing. And the statement of the covariant entropy bound is that you get to pick any surface you like. It doesn't even have to be closed, actually. You can always look at all these four null directions away from it. Pick any of the ones in which the area is decreasing, and then that's a light sheet. And on any light sheet, the total entropy of matter that light sheet intersects is less than the initial area divided by 4. That's the conjecture. Okay, so in a way, it's, well, we'll see how this applies to the cases that we're interested in. And here's a spatial view. So now I have projected time out. And this is an example of a situation that would lead to a light sheet. So if your initial area is A, you follow the light rays for a little bit away from that area. You look at the new area that's spanned by them, by these light rays. If it's smaller than what you started with, you're okay. You've identified a light sheet direction out of these 4. And there are always at least 2, assuming that the null energy condition holds, which is a very weak assumption on the energy density of matter. And the reason is pretty clear. If this is a sphere, well, the light rays that go towards the future and towards the inside are just continuations of the light rays that came from the past from the outside. So if these guys, for example, are expanding, then these are necessarily contracting unless the surface that you started from happens to represent a local minimum of the area along the light rays. And there are no local minima of the area along light rays if the null energy condition holds. Light rays can never do this. They can never span a smaller and smaller area and then start growing again in area. They just can't. That would be, that's guaranteed by what's called the focusing theorem. Once light rays are contracting, the only way they can start expanding again is if they first intersect each other. Okay, so that guarantees that there are always at least 2 directions which are contracting. And there could be more if this surface happens to be a local maximum of the area. Of course, the intuition I've developed so far was based on flat space, on Minkowski space, where the 2 light sheet directions are the obvious ones, where the light rays are going towards what you would ordinarily call the inside of the room. But in cosmology, in inside black holes, it's not always so obvious what you mean by the inside, and this gives you a general definition of such a notion. So here's an example. Here's a closed universe, and what I've drawn here, these little wedges, they tell you which way the light sheet directions go. Remember, every point in this diagram represents a 2-sphere. A line across represents a 3-sphere. I showed it here on the blackboard earlier. So, for example, this point here at the tip of this wedge is a 2-sphere at the turnaround time. So the universe is actually momentarily static. And because it's static, it's clear that the directions in which the spheres are going to be shrinking are towards the, well, if I'm close to the North Pole, it's going to be the directions towards the North Pole. This tells you that, in some sense, you know, the inside of some circle near the North Pole is, well, the polar cap and not this huge region out here. Okay, we could have gotten equally confused about what the inside of the walls of this room are, right? Maybe they're the whole rest of the Earth and not this room. But no, it's not. It's according to this rule, it's really the polar cap if you have a small circle near the North Pole. But it doesn't matter whether you send your light rays towards the future or towards the past. But look here, for example, near the Big Bang. Okay, if I have a large sphere near the Big Bang, then it in fact doesn't matter whether I send my light rays towards, you know, the inside or the outside in the spatial sense. If I want them to decrease, I have to send them towards the past because the whole universe is decreasing so rapidly towards the past that that's the most important effect. And you can see that that has to be true by just thinking about the equatorial sphere at that time, where there's clearly no distinction between the spatial inside and outside, but the universe is expanding, and so it must be favorable to send your light rays towards the past if you want them to decrease in area. Okay, so that's why this wedge here is pointing, I mean, the legs are pointing down. Those are the allowed directions. And then you can see by symmetry, of course, near the Big Crunch, they have to point towards the Big Crunch. If you're near the South Pole, they have to point towards the South Pole. Okay, so these diagonal lines here are just the boundaries between these different wedge domains. So every sphere in this region here is what I would call normal. The inside direction is, it doesn't distinguish between past and future. There's just one side towards which areas get smaller. That's the situation that we're used to from non-dynamical geometries, from flat space. These spheres here are called trapped, anti-trapped, and these up here are called trapped. So they are weird kind of spheres that you have in curved geometry. Okay, so the difference between what I've now written down and what I was doing earlier is that earlier I was trying to sort of derive entropy bounds, and it didn't quite work, but that's why in the end I have to do this. But I started with something like the second law of thermodynamics, which we all like and believe in, and then, you know, what can you derive from that? Here, this is completely the opposite viewpoint. This is just a statement that appears to be true. It's far more general than what I could have derived by considering dropping matter systems into black holes. At least, I don't know of any such derivation. I don't think there can be one. And so I think we should look at it just as a hypothesis, as a conjecture. We should see if it's true. We should check it case by case, not just with real matter systems, but with pretty much anything we can imagine building in our head, subject to the laws of physics, of course. And it does seem to be true. And so that's curious. So now you have something that's quite a non-trivial statement relating entropy of matter to area of surfaces. And it's always true, including inside black holes, as we'll see, and in cosmology. And so it begs for an explanation.
Sorry,
yeah.
When you say solve the Einstein equation, you mean the Einstein equation is this method?
Yeah, right. So you have to, exactly. So the only reason that it has a chance of being true is that you have to consider the back reaction on gravity. And that's what saves it in the end. Now, it's not obvious that it does. In other words, it feels like a conspiracy a little bit.
But I mean, if there are some corrections, I mean, higher curvature corrections.
Oh, well, we can certainly think about higher curvature corrections and things like that. But we can certainly test this in a very large arena where it's just Einstein gravity coupled to matter. And that's a highly non-trivial statement just in that arena. You can see that from how easy it was to find counterexamples to the space-like entropy bound and to lots of other proposals that I didn't have time to go over. Right? It's not hard. The reason that, if this is going to be wrong, it's not because of higher curvature corrections. It's going to be wrong in a blatant blow-up-in-your-face kind of way.
So this is mainly related to general coordinate environments, or Einstein equation with classical kind of way of theory?
Well, it's an interplay between classical Einstein equations and the information content of matter, so basically quantum mechanics, which is which can be tested in a regime where quantum field theory coupled to Einstein's equations is a good approximation, but which I don't think can really be understood from that viewpoint. To understand it, I think you need some theory that builds this relation in from the start. The very optimistic way of presenting that notion is to say, look, we've come upon a conspiracy. We've come upon something which it's not it's not a contradiction with the theory we have. We can check that these bounds are satisfied using quantum field theory coupled to Einstein gravity, using this approximate description of nature. Just as we can easily implement the equivalence principle by just simply tuning the gravitational mass to be the inertial mass in Newton's theory. That's not the problem. The problem is that it's crazy. Why? You have to explain why that is. It seems completely arbitrary. The theory doesn't demand it. You have to put it in by, So that's really the hope. The hope is that this could help. It could be a guidepost. Probably we need others. But it's something that constrains the quantum theory of gravity in the sense that you would expect that the underlying theory that really explains nature will have this kind of relation built in from the start. It'll make it obvious that there are just not more degrees of freedom in nature than an area's worth for the description of any light sheet. And in the way that say, general relativity made it obvious that all bodies fall at the same rate because they're just following geodesics in curved spacetime.
This entropy works also for the classical systems, for hot gas and something like this.
Well, they're not, the entropy itself is really a property that's quantum mechanical, but the systems are classical in the sense that they're you can treat them thermodynamically. Their back reaction so that the curvatures are not high, so general relativity can be treated classically. Curvatures are very weak, arbitrarily weak, and we can test this nevertheless. Right. Any other questions? Okay. So I think that a theory that really explains this has to know about quantum theory, it has to know about gravity, and it has to know about the matter content. Because I guess this was already clear in some of the remarks. If you had certain types of matter around that we don't think exist, you could easily violate all these entropy bounds, including the covariant bound, because the way that they work is by the back reaction of gravity to your attempts to put too much entropy in a region. But you could always cancel that if you had things like negative mass. Right? If you had objects which violate standard energy conditions, which we don't think exist in nature, but if you had them, then you could violate these bounds. And so in the end, there's clearly some connection between you can't have these bounds in a completely arbitrary quantum gravity theory. A particular sorry.
It's also when you have the cosmological concepts, both positive and negative.
Well, so there are types of matter which have negative energy density, which we don't believe are pathological, and a negative cosmological constant is an example of that. But those happen to not allow you to violate these entropy bounds either. So here I would say that the problem is rather that we find it very hard to characterize what constitutes legitimate matter. And these energy conditions are a very crude attempt at capturing that. And in fact, a negative cosmological constant does not violate the null energy condition, for example. It's okay with that. One challenge in finding a theory that will explain the holographic principle, that will explain this relation, is, of course, the tension that is inherent in this location, in this relation between locality and the fact that the number of degrees of freedom seems to scale with the area. Locality, quantum field theory, it's a very successful theory, and it tells us that we can adjust degrees of freedom independently in different regions of space. And gravity, at the same time, somehow has a very holistic view of what's excited. And you can have a fairly low density. If you have it over a large enough region, you'll make a black hole. So that's a big tangent. And so you have to explain both this area scaling, but at the same time retain some understanding of where locality is coming from and to what extent it's a good approximation. This actually I could probably skip because I already commented on it in response to one of the very good questions earlier. But what do I mean by the entropy in the context of the covariant entropy bound? Well, generally speaking, what you would mean by entropy of, I don't know, a star or this or that matter object, more or less implicitly you're including some coarse graining parameters. You're saying, well, by a star I really mean an object of this and that temperature occupying, you know, this and that volume, you know, maybe a few more specific constraints, and then how many quantum states are compatible with that. Take the log of that number of quantum states, that's the entropy. In this case, it's a little harder to understand what fundamentally the entropy should be. It seems to me that there's one obvious constraint that is being imposed in the formulation of the bound itself, which is that the systems fit on a light sheet of a given surface of area A. And so, well, that might be the only one. That might be the only constraint. In practice, we usually impose additional constraints. For example, we hold the approximate background metric fixed. When we look at entropy bouncing cosmology, we first pick the universe we want to deal with. Then we pick a sphere or some surface in it. And then we check if the entropy is bigger or smaller than that area. And of course, you know, you could have a situation where the bound passes this test, but would fail if you really included all the different background spacetimes that surface could be part of. And I don't know, right? But again, I take encouragement from the fact that, you know, it's certainly a necessary condition for these bounds that if I hold the background fixed, I don't get to violate them. And in formulations of entropy bounds that failed, that was already enough. Those kinds of tests were already enough to rule them out. So I hope that that's you know, that's going to be sufficient. Let's see. Yeah. So here I just want to emphasize that it's not important that we consider a closed surface. You can really take any area element, right, and you'll have 4 null directions orthogonal to it. And you know, then at least two out of these 4 will be non-expanding, and you can follow those light rays, and they'll make a light sheet for you. When do you stop? That's another question. Well, actually, you don't need a separate criterion for that. This non-expansion criterion is already enough to tell you when to stop. You stop when that criterion becomes violated. When does it become violated? Well, by the null energy condition, it only becomes violated after the light rays go through a caustic. If you don't think the null energy condition is satisfied, well, then just use that criterion directly. If light rays, after all, can do this kind of bouncy thing, well, you stop when the area starts increasing. This expansion is not just something that I have to define with my hands moving. It's defined in the usual way, that the same way that it would be for time-like congruences. This is really a congruence of null geodesics that I'm talking about. They have a tangent vector k. You can define really the divergence of that tangent vector is the expansion. And intuitively, you can think of it as the logarithmic derivative of an infinitesimal area element as it's transported along the light rays. An area element spanned by the light ray and its immediate neighbors. If that area element gets smaller, you have contraction or negative expansion. If it gets larger, you have positive expansion. And at focal points, it diverges to negative infinity. This concept of expansion also plays a huge role in singularity theorems. Okay, so I think, well, I've gone through this, so let me just repeat the bound again. So you pick any surface B in the spacetime, you construct any light sheet of it, and you look at the entropy of all the matter systems that intersect that light sheet, and that's less than the area. That's the conjecture. Are there any questions about the actual statement?
When Bekenstein started, he put an eta there.
Yeah.
And you put a 1/4 for the eta. Are there any of the examples where this is important that it's...
Yeah, there's one. You're right, it's a good question. What fixes the 1/4, since it's pretty hard to well, okay, let me say this now. So if you wanted to saturate this bound, it's pretty hard, right? We already know that for static matter systems like thermal radiation, which seems like it's, among static systems at least, it's the most entropic system we can make for a given mass. The maximum entropy goes like a to the 3/4. So for large systems, you miss by a huge factor, a to the 1/4. The bound is satisfied with a huge amount of room to spare. So then, why couldn't this 4 be 10 or 1 million? Now it's actually the case, as we discovered only in 2009, so much later, that you can have a light sheet with matter entropy on it that's of order the initial area. So you can beat this a to the 3/4 with highly dynamical systems. So there, it's really important that you make use of time dependence. One thing you can do is take a piece of an open universe and time reverse it. So that's basically a bunch of collapsing matter particles. And then certain light sheets in that geometry will have entropy of order the area on them. You can't clearly violate the bound, but it looks like it can come to within order 1 factors of saturating it. That still doesn't fix this 1/4. So I don't know for sure that it should be a quarter. There's one aesthetical reason why a quarter is natural, and that's the following thing, which was noted by Flanagan, Maroff, and Wald soon after I conjectured this bound, which is that really the generalized second law can be viewed as a special case of this conjecture. And the generalized second law is also a conjecture. It's a conjecture that the area of a black hole always more than makes up, or at least makes up for matter entropy that goes into the black hole. But that's contained as a special case in this statement, because what happens if I choose my initial surface of area A to be on the horizon of a black hole? Right, so I get to apply this to any surface, so I get to apply it to that as well. So first of all, what are the allowed light sheets? Well, the horizon of a black hole is a boundary between a trapped region and a normal region. Inside the black hole, all surfaces are trapped, at least the ones that are outside the matter system that made the black hole. Here's the matter system that made the black hole. And so the light sheet directions here, there's actually 3 of them. I could go this way, I could go that way, I could go that way. Let me go that way. So I'm going to build a light sheet like this. Okay. That light sheet is probably constant area for a while if nothing fell into the black hole recently. And then at some point, going back in time, it sees the matter system that made the black hole, and it contracts down to R equals 0. That's by construction how it has to work, since I've picked it to be on the horizon. Okay. And so the entropy that is on that light sheet is the entropy of whatever matter system made the black hole. Okay. So that being smaller than the area over 4 is precisely the statement of the generalized second law for black holes that form from the collapse of a matter system. So it makes sense to match it up. But that's there's no, that's the only argument for the 1/4.
This holographic principle works also in different dimensions? Or?
Yeah. The area by area, you then always mean something of codimension 1 + 1 in the space-time.
But what about 3 dimensions?
Well, yeah. Gravity is...
Yes, I know. This is one of the questions.
Gravity is yeah. So in examples where gravity is still interesting in 3 dimensions, it seems to be well, so you know, if you have something like ADS3 cross something else, then you know, you have black holes, you have the notion of entropy. It seems to be satisfied, but it's hard to come up with good examples testing the bound in those situations. And okay, you know, yeah, it's a good question, but three-dimensional gravity doesn't seem to be a particularly interesting setting as far as I know for studying these bounds. But I may be wrong. You know, I haven't really tried that hard. Yeah.
Why you call this entropy bound covariant?
Ah, good. Why do I call it covariant? Well, I call it covariant because its definition actually makes sense in arbitrary spacetimes. It's not defined in a way that doesn't make sense in arbitrary spacetimes. When people said the entropy of a matter system is less than the area of the surface of the matter system, that's not a covariant definition, because to define the area of the surface, as my example illustrated with these zigzag boundaries, actually depends on picking a particular time slicing. So it's not, so the very statement of the bounds that were conjectured was not covariant. And that's why I secretly believe they had no choice but to be wrong. Okay, so I think it was important to just formulate something that even makes sense in general spacetimes. Or think of the closed universe. The entropy inside a surface is less than the area of the surface. Well, what do you mean by inside in a curved geometry, in a closed universe, right? You have to start by saying something that makes sense at the geometric level. And so anyway, that was the reason why I picked that name, but I don't think it was a very good selling strategy. Sound really boring. All right, so yeah, in a Penrose diagram, I just want to, good, I just wanted to, sorry, I did this on the blackboard already, so forget it. Yeah, so let's go through these. Remember, we had 4 examples of arbitrarily bad violations of this space-like entropy bound, this straw man that I set up earlier. And I want to go through all of them and see how things play out with the covariant bound, just so you get a feel for how it evades these problems. So forget the right picture for a second. Just remember the left one here. This is an instant of time. This is a 3-sphere. This is a 2-sphere near the North Pole. And what we were doing is we were saying, well, I can make this entropy, which is enclosed by this surface, this blue surface, I can make it be arbitrarily large, the blue surface arbitrarily small. I got a problem. Well, if that blue surface is very small, then we're dealing with a situation where that in the Penrose diagram, the blue dot is very close to the North Pole. And so the allowed light sheet directions are the green things here. They're normal. They're towards the North Pole. And this red region here really corresponds to this line here. And it's not an allowed light sheet direction. Away from this blue dot, the area initially increases as I go towards the past. The same thing would happen if I tried to do it this way and go towards the future. I'd have the same problem, that it's not allowed by the bound. You're not allowed to consider that. I mean, you could find an entropy bound on the matter on this red line as well by looking for the maximal area on it, which is right here. Right, you can see it's right here because that's where the wedge directions flip. So if you're sitting here, then this guy here going to the up and right is an allowed light sheet. This guy down here is also an allowed light sheet, so I guess you would say the entropy has to be less than this area divided by 2 instead of 4, because you have to use 2 light sheets to really cover this red line. Okay, but what it doesn't have anything to do with is the area of this blue dot. Okay, it's just not a light sheet of that blue dot. Did I explain this well? Okay, so yeah. So it's kind of important, or at least the way the bound is formulated is you start with the area, and then you construct some 2+1 dimensional null surface away from it where you look at the entropy. You don't go the other way around. You don't say, oh, I want to look at the entropy in this and that region. You can do that too, but then, you know, it becomes a game of, well, what's the cleverest way of choosing an area such that that entropy is contained on its light sheet? It's less direct. Okay, so that works out. Well, I should make a disclaimer. You can check that this really does work out at the quantitative level, and I'm not going to do that here. All that I'm going to try to convince you of is that the obvious violations that I had earlier on are no longer possible. Okay. Earlier on, I could show that the space-light bound was violated by arbitrarily large factors, and here that's not the case. If I move my area too close to one of the poles, then I'm only allowed to look at light sheets that go towards that pole. Here's a flat Friedmann-Robertson-Walker universe. That was our second example. Remember, we were going to look at one instant of time, which I should have drawn into this picture. It's a line like what the red dot here is following. That would be an instant of time. This corner here is really infinity. So this instant of time corresponds to infinite flat space. And what happens if I look at larger and larger spheres? It's true that the volume goes like radius cubed, the area only like radius squared. So why am I not in trouble? The entropy density is constant. Well, I'm not in trouble because if I make the spheres very large, larger than the apparent horizon, then the allowed light sheet directions are towards the past only. And if I go towards the past, then what's going to happen is I run into the Big Bang. And so my light sheets are not, in fact, going to see all the entropy that's inside. So let me draw this on here. Okay, here's the Big Bang. Here's a very large ball of radiation, let's say. Okay, and the entropy that's causing me trouble is all the radiation that's, well, in this ball of radiation. Okay, that is bigger than this area. It's sigma r cubed. Okay, but here is the allowed light sheet. Okay, it doesn't actually, so if we assume adiabatic evolution, then the entropy is independent of time in any given co-moving region, but the only co-moving region that I pick up is this region. And that's basically a shell of some fixed width given by the horizon scale at this time. If I make the sphere even larger, well, I pick up this region. Okay, it scales like r squared times the fixed width. It doesn't scale like r cubed anymore. So it's okay. Again, quantitatively, you have to check that it's okay, but you can see that the scaling no longer allows you to argue that there's a problem. The collapsing star is almost like a time reverse of this. Here's our collapsing star. Remember, you had a lot of entropy here, very small area there, arbitrarily small as I approach the singularity. But this light sheet here is what's allowed. You have to have future-directed light sheets only. I'm not allowed to consider a past-directed one because we're in a trapped region. And again, you find that the thing just doesn't get far, it doesn't get deep enough into the star. It only sees some outer layer of the star. And as I look at later and later times where this area is getting smaller and the surface area of the star is getting smaller and smaller, I see a thinner and thinner layer. The light sheet is picking up less and less material until it gets truncated by the singularity inside the black hole. Okay. So, this is really gravity sort of dynamically conspiring to prevent violations. Wait, what do I do? Oh, this. Yes, and then, oh, good. And then the nearly null boundaries. That was the sort of nerdy example at the end that really exploited general coordinate invariance. And what happens here? So I can surround this room by an arbitrarily small area by boosting my time slices in very sick ways. And what happens with the light sheets in that case? The light sheets, in a normal way of slicing time in this room, at an instant of time, you look at light rays orthogonal to the wall, they would go really orthogonal to the wall also in the ordinary spatial sense. Okay? But if you look at a highly boosted way of slicing the walls of this room, then the light rays orthogonal to those slices they do not, in a spatial sense, move orthogonal to the wall. Okay, they kind of move off sideways. And they move with a sharper and sharper angle off sideways. So if you project what they see onto a spatial slice, it looks like this. And in the limit where you make the area go to 0, what they see of the room also goes to 0. Again, you have to check that it works out quantitatively. I'm just showing you that things scale in the right way. Okay. So, so let's say this is right. So we want some quantum gravity theory that explains this, that maybe has only an area's worth of degrees of freedom to describe matter on any light sheet. Well, it looks like we've had some luck with that. We have a quantum gravity theory in asymptotically anti-de Sitter spacetimes. And so is it holographic? Does it have this property that one would hope for of making this bizarre relation completely obvious? And the answer is yes and no. The answer is yes if you look at large enough spheres in this ADS space. Well, first of all, let's ask about the correspondence. So the correspondence is basically you have a conformal field theory which you can think of for convenience as living on the boundary of this anti-de Sitter space. Anti-de Sitter has this very funny boundary that's really time-like. It's very convenient for this way of thinking. Every instant of time in the bulk really corresponds to an instant of time on the boundary. Other spacetimes aren't like that, which is a big problem. And you have a conformal field theory living there, and there's a certain dictionary that tells you how to translate states of that conformal field theory or operators in it into statements about string theory in the bulk or semi-classical gravity in the bulk. But because the conformal field theory is completely well defined, at least we're pretty sure it is, it's a non-perturbative completion of string theory in the bulk. And so it really defines a complete theory of everything that happens in the bulk in terms of something that doesn't even have gravity in it. This conformal field theory is just a field theory. So you could put it on a computer. You don't have any conceptual issues there. Just run it. And it does the trick. Now, the number of degrees of freedom in the conformal field theory, if by number of degrees of freedom I mean the log of the dimension of a Hilbert space, is of course infinite, as it would be in any local field theory. And the maximum entropy in the bulk is also infinite. The areas of spheres at the boundary are infinite in anti-de Sitter space. And so there's no contradiction, but it's also, well, kind of a stupid statement that, well, the fact that infinity is equal to infinity doesn't give us much evidence that, that the holographic bound is somehow made manifest. But it turns out that there exists, at least at a pretty good approximate level, a cutoff version of this correspondence that's still valid. I could ask, well, what if I'm only interested in describing anti-de Sitter space out to some large radius, but not all the way out to infinity? So if I'm willing to concede that in the bulk, do I get to throw out some stuff from the CFD in exchange that I might not need? And the answer is yes, I do. I get to throw out certain UV degrees of freedom. So roughly an infrared cutoff in the bulk, restricting to a certain size region in the bulk, corresponds to putting a UV cutoff on the boundary theory. And you can, in fact, construct the UV cutoff geometrically. You just think about propagating a signal in from the boundary and asking, well, how much has that thing spread by the time that that light cone first touches my green bulk region that I actually want to describe? And then you can just argue that really anything that's shorter wavelength than that cone than the size of this light cone on the boundary at the time when it first penetrates this bulk region, I really didn't need that. Right? I didn't need these short wavelength degrees of freedom because I couldn't have probed that green region at all yet. This is really a longer argument, but it gives you a notion of what. The relation is really very simple and very geometric. So you can see if I'd made the the green region smaller, it would correspond to a longer scale, so lower energy scale boundary UV cutoff. This is called the UV-IR relation. And because there is this relation between cutoff versions of the bulk and the boundary, I can now actually check whether the theory is holographic. I can ask, well, what is the entropy I can have in the conformal field theory with a certain cutoff? It's actually a cutoff on the energy density I have to apply, but that seems to be the right thing to do in the CFT. And I can compare that to the area of these spheres. We're dealing with normal spheres, so light sheets will just go in and see all the stuff in the center. And the answer is they're the same, at least up to order 1 factors. Okay, so the area as a function of the UV cutoff, the area of the green sphere here it's the right number. Okay. So the holographic principle is manifest in ADS CFT, except, of course, this works for, sorry, let me go back for a second. This works for sufficiently large spheres. It doesn't work for other surfaces of different shapes, and it doesn't work for small spheres. So suppose that, I have some anti-de Sitter space with, so it's a maximally symmetric spacetime. It's characterized by some curvature scale, L. But I can make that scale large. I can make it be, a billion light years. And once I make this green cutoff region smaller than the ADS curvature scale, so I basically zoom in on something that's less than the central ADS 1 curvature volume, this correspondence really is too inaccurate to tell me anything useful, this UV-IR correspondence. So I don't have a way of understanding in some totally manifest way why I need only, a quarter of the degrees of freedom, why I'm using only a quarter of degrees of freedom to describe, a sphere that's half as large once I'm in this regime of relatively small spheres. So it's a limited, it does make the holographic principle manifest in that for these large spheres, it's clear that the fundamental theory has just the right number of degrees of freedom that's allowed by holography. It's completely clear that you couldn't possibly violate any of these entropy bounds because you just don't have that many degrees of freedom in the theory to start with. You're very happy. But it's not actually true that it's manifest for all surfaces in ADS. You have to look at large enough spheres. Okay, so it's encouraging. But it would be nice if there was some other more general formulation of the theory which makes it manifest in all cases. It'd be nice especially because it might help us in other spacetimes. So what have we accomplished and what have we not accomplished? One thing that the covariant entropy bound tells you is that the world really is like a hologram. Even in spacetimes which don't even have a boundary. If you phrase the statement of the holographic principle in the language of, well, the correct theory lives on the boundary and has an area's worth of degrees of freedom, it's hopeless, right? In cosmology, there doesn't have to be a boundary. But it's always true that you can slice the spacetime, for example, with these slices like this. And for every slice, find an area which is larger than the entropy on the entire slice. Okay, so this would be the apparent horizon in this spacetime. So in this case, the boundary lives inside the spacetime. That's the price you pay. But it is true that you could, literally put zeros and ones with a Planck density on this area and specify everything about the quantum state on every slice, sort of in the bulk. Okay, so that's a non-trivial statement. What we don't know is how the encoding works. So we don't have any analog to this incredibly rich and specific statement of the ADS-CFT correspondence in most spacetimes. In fact, there are many huge problems in imagining how such an analog could possibly work, but that's just a basic problem of quantum gravity. It's not clear what exact observables are and so on. And in a way, the holographic principle makes it clear that that's a very general obstruction. If you have access only to a finite space-time region, well, you have a finite entropy bound. That means you can't write down a number with arbitrarily many digits. So it would be very surprising if you had any exact observables like the S matrix or correlators in a CFD in a fundamental theory. What would such a theory look like? I don't know. Okay, so ADS is special. The holographic screen in ADS is out at the boundary, and it has lots of beautiful properties. It has constant area. Maybe it's not so surprising that we understood how it works there first. In a general space-time, the holographic screen that I constructed in this way by basically following the wedges towards their tips. So you go to a large area on every slice, and you find a screen. That does not have, those kinds of screens can be space-like. They don't even have to be time-like. The area need not be constant. We should probably not expect there to exist a unitary quantum field theory that somehow evolves on such slices at a degree of freedom per Planck area. So it seems like there's some challenges that this spells out for us. Are there any questions before I move on? Yes.
How could you imagine of applying the covariant entropy bound to de Sitter instead?
Well, again, of course, you can apply the bound to anything, to any surface in any space-time you like. Good. The question, I'm sure, is what does it teach you? And so let's consider de Sitter. So for those of you who haven't heard too much about de Sitter space, it's the maximally symmetric solution with a positive cosmological constant. You can think of it as a closed universe that's contracting and then expanding like Kashif time. And its Penrose diagram looks like this. It's a square. And its wedge diagram looks like this. These regions are normal. These regions are trapped and anti-trapped. Singularity theorems don't apply here because the positive cosmological constant violates the strong energy condition. So even though you have these trapped region, these trapped spheres collapsing here, they don't make a singularity. So, well, there's many different things you could do. I like to think of cosmology generally, but de Sitter space in particular, in terms of what one observer could see. And what one observer can see or probe is limited quite generally by, well, take the observer's world line, extend it as much as you like, give them all the time they want. But what they can really control and probe is what's within what's called the causal diamond of the observer. So basically the intersection of the future light cone of the starting point with the past light cone of the end point. That region is what you can actually access. Maybe you have a flash of light that comes in from here, but you have to get lucky. And if it does, well, it's part of what's in this region. Maybe it doesn't go that way, then you don't see that thing that's down there. So this is really the region that you should focus on. And so if I do that in de Sitter space, it's this causal patch here. It's what's called the static patch in de Sitter space. It is what is foliated by the static coordinate system that you can write down for de Sitter space, which is similar to the Schwarzschild coordinates. So now I can ask, well, what does the covariant bound tell me about that? I didn't really need the covariant bound because I could have just noticed that this is the horizon of de Sitter space. And if some sort of generalized second law holds, it had better be true that whatever matter I had in here had entropy less than the final surface area here in some asymptotically de Sitter space-time. That's 3 pi over lambda. That's the area over 4, and lambda is the cosmological constant. So what does this tell me? In de Sitter space, I live in a spherical box of this area. And the matter I could possibly have around has to have less entropy than that. Of course, the covariant entropy bound reproduces that result. You can just pick this area and look at this light sheet or something like, pick this area and look at this light sheet. And it'll reproduce that, but it doesn't tell you really anything terribly dramatically new compared to what you already knew from just the Gibbons-Hawking entropy of de Sitter space. In this case, you have an actual, it's a bit like recovering the GSL for black holes. You already had some understanding that came from the thermodynamics of killing horizons. There was another question up there, yeah.
Do these screens always necessarily have to be topologically equivalent to a sphere?
No, and as yeah, right. I noted this earlier that they don't even have to be, oh, the screens, sorry. So the surfaces you pick don't have to be closed. The screens, no, they don't. I don't think they have to be topologically equivalent to a sphere. There's a huge, well, I'm tempted to call it gauge freedom, but let's call it ambiguity in the construction of screens. What I did in the examples that I showed was, first of all, I started by considering spherically symmetric spacetimes like this closed universe, or, a black hole that forms from spherically symmetric collapse. And I constructed the screens by basically constructing first a null slicing of the spacetime. And there's a huge amount of freedom in doing that. I did it by looking at all the past light cones from r equals 0, but I didn't have to do that. I could have done some other construction. Because they're spherically symmetric, of course, then the maximum. So what you're looking for is along each past light cone, you're looking for where the area is maximal, and that's going to be your screen, because that's where you can, if you started with their surface, you'd have a light sheet going, then you can reconstruct this slice as two light sheets. Right? That's what's happening here, for example. The upper half of this slice is one light sheet of this area, and the lower half is the other light sheet of that area, and you have a statement. And so by construction, it's not very surprising I got spheres for the screen, but I could imagine that in more complicated spacetimes that's not the case, and I could find other examples. I don't see any fundamental significance. Sorry?
It doesn't even have to be closed?
I don't necessarily see why it'd have to be closed. Well, okay, I'll give you an example. In Minkowski space, it's of course a very trivial example. But in Minkowski space, the hypersurface z equals 0 is a screen. Right? It's so yeah, and that would have planar topology. Good. Other questions?
What is the role in your description of the conformally variant mapping which Witten gave from de Sitter to the conformal boundary, which is explicit and...
Yeah, so I was focusing in my answer to the earlier question about de Sitter space, I was focusing on the static patch, thereby completely excluding my access to the conformal boundary. I do suspect that that's probably going to be the right way of thinking about de Sitter space. But you can, of course, consider spheres out near the boundary and consider light sheets from those spheres, so they would be going towards the past, either this one or that one. And in some approaches to quantum gravity on de Sitter space, like the ones that Ed pursued for a little while and that Andy Strominger pursued, those seem to play a much more important role than the static patch. But I don't really have anything more to say about it. I mean, the covariant bound is satisfied on those light sheets. It tends to be satisfied with a lot more room to spare than in examples that I can construct for the static patch, which is another reason why I believe that these are probably not the right places to consider constructing a theory at, but I wish I could say more about de Sitter space, but I can't. Yeah?
In string theory, you can have geometric and topological transitions between different spacetimes. Do you allow for those in the bound, or are there known examples where you can follow this?
Right. I've emphasized this a few times. So I think ultimately, yes, ultimately this should all be part of a holographic description of space-time. But what I'm trying to get at here is something else. I'm trying to say that even in semi-classical gravity, we have what seems like an extremely surprising relation between area and information. One which, it looked for a while, had no chance of being correct because you could find all these very violent counterexamples to it. But once it's formulated in terms of null hypersurfaces, actually, seems to hold up. And that alone is something that really I find very striking, that it seems to me requires an explanation. But in situations where I have to have a deeper underlying theory to understand the geometry, like, I don't know, a flop transition in string theory or something like that, I'm not sure that this will, add anything to the story that you didn't already know. I certainly wouldn't know how to do that. All right, thank you.